Good afternoon, everybody. This is Valeria Bertacco. I'm the technical program co-chair for DAC, and it's my pleasure today to introduce Chris Razanovic, who will be presenting RISC-V Instruction Sets Wants to be Free. Chris is a professor of electrical engineering and computer science at University of California, Berkeley. He received his PhD in 1998 from there, and then went to be a professor at MIT. I found that to be a little bit too cold for his taste. So after 10 years, he came back to Berkeley, where he co-founded a whole lot of stuff, from the parallel computing lab to being associate director at the Berkeley Wireless Research Center lab. But the most important activities that relate to this talk is he founded the RISC-V ISA project and is chairman of the RISC-V Foundation. And he has co-founded Sci-Fi Inc. that supports the commercial use of RISC-V. So he is at the core of everything that relates to RISC-V, and he will present today what it is about and how we can use it. Enjoy.
Okay. Thanks, Valeria, for the introduction. Okay, so I'm here at DAC to tell you about an instruction set. And probably most of you are worrying about, how do I get my 7-nanometer FinFETs to do the right thing? So why are we worrying about instruction sets? Well, sort of dive right in and just ask a few rhetorical questions of, why do instruction sets matter? Well, why can't Intel sell mobile chips? Right? It's because nobody wants an x86. They're all happy with the ARM instruction set in those phones. They're not going to port the software stack over. That's probably the biggest single reason. There may be some other technical ones. It's not like it's all rosy in ARM's land. Why can't ARM partners sell servers? Well, it's because everybody wants x86 ISAs there. In particular, the AMD x86-64 ISA that's used in nearly all the servers that are built. And it's an interesting story. Why is it an AMD ISA that's being built by Intel for the majority of those servers? Well, Intel tried to force a different ISA, Itanium, on the world in hopes of shaking off the second source AMD, right? So, my sources tell me that Itanium was primarily an anti-competitive measure, right, to introduce a different ISA. Luckily, that failed, so there is some choice. Not much, though, in the server land. Another question, how can IBM still sell mainframes, right, and make a lot of money doing it? Again, it's because of the ISA, right? So 360 is the oldest surviving ISA, more than 50 years strong, and it's still the core of a multi-billion-dollar business for IBM. So the ISA is the most important interface in a computer system, I'd argue, and the reason is it's because where software meets hardware at the ISA. Right, so the most important interface. Now you can see here the ISA basically divides up the computer industry, right? You segment the industry by the instruction sets. It gets even worse if you look at a modern SoC, because a modern SoC has many, many different ISAs on a single chip. So what you'll find is the ISA you know about, like you have an ARM chip in your iPhone, that's what the software is coded to. But as well as that visible ISA, there are all the other ISAs on the chip in the graphics processors, image processors, radio DSPs, audio DSPs. There's all these other ISAs on the chip, and I've heard, tales of there's more than 12, 15, 16 different ISAs on a single chip, right? And part of this is because why don't they all use the ARM or the x86? Well, it's too big an ISA, it's too clunky. You don't want to base these accelerators around there. It's also proprietary and expensive to license. So some of these ISAs arise because companies home-grow their own one for some little purpose, and then they find they have to stick with it over many generations. Okay, so do we really need all these different ISAs? The question, do they have to be proprietary? What if there was one free and open ISA we could use for everything, right? And that's really the premise behind the RISC-V project, okay? Now, it's kind of curious, if you look inside most products today, they're built around open standards. So there's a great paper I urge you to go find from professors at Arizona State, one of which is general counsel at Intel. They looked at a modern laptop and took it apart and looked at all the standards that go in to build a laptop. And there's something like 500 or 600 different standards, the vast majority of which are open, right? One of the exceptions being the ISA, right? If you look at these different areas of computing, in networking, we have Ethernet, it's a standard. There are both proprietary and open source implementations of both Ethernet hardware and the software stack that drives it. The same for operating system interface, like POSIX, right? You have free implementations of it, like Linux and FreeBSD. You also have proprietary implementations, like in Windows 10. Okay, going all the way through databases, graphics. We have a standard, we have both proprietary and open source implementations. But at the ISA level, we have x86 and ARM. So for the most important interface, it's not open. And what's worse is the ISAs we do have are pretty dismal. They're not, we didn't pick these because they are great for any reason. Just historical legacy reasons we're using these interfaces. Now, we're not the first people to propose an open ISA. To give some credit, way back in the early days of SPARC V8, they made that an open standard through the IEEE. It cost just $99 to get a license to build SPARC chips. And Sun and a few other companies provided open source cores to implement the SPARC ISA. However, that ISA is now owned by Oracle, so future developments are proprietary. Also, SPARC has a few issues if you actually try and use it in systems as an ISA, technical issues. Another effort was OpenRISC, and this was started by a bunch of Slovenian undergraduates who took Dave Patterson's, John Hennessy's book, the DLX design from there, and basically typed it into Verilog and created this OpenRISC core that actually got reasonably widely used. At the time we started RISC-V, we looked at this and realized it again had a bunch of technical issues, and also they didn't have a 64-bit version when we started the project. Okay, but for technical reasons, as well as where they were at the time we looked at this, we didn't think these actually met the needs of a free and open universal ISA. So for us, we believe the requirements you're going to need for this universal ISA, it should work well with existing software stacks and languages. You know, we're academics, we love to try new things, but if we come up with a wonderful new instruction set that requires, you know, for example, it doesn't support C compilation, you know, that's a non-starter. It has to be an ISA that actually works with all the software that's out there. It has to be a native hardware ISA and not some kind of virtual machine or an architecture-neutral distribution format. Those are solving a different problem. You actually need to build chips. You need to have a standard ISA. If you try and go one step up and have a letter of indirection, what you find is everybody spends all this effort building that mapping down to some custom hardware ISA and have to repeat it. You really need a standard real hardware ISA. We want to support all sizes of processor, from the tiniest microcontroller up to the largest supercomputer, right? And all implementation technologies, from FPGAs to ASICs to full custom. You might ask, why do you want to support such a breadth of things in a single ISA? And the reason is for software. The more reuse you get from the software layers, the more software will be available in any of these application areas, right? So you want the maximum reuse of everything you do at the software level, so make an ISA that doesn't preclude it being used in all these different application areas. We also want to make an ISA that's not tied to any particular implementation style. Some of the commercial ISAs, the problem has been the architects were just looking forward at very high performance implementations and weren't thinking about the smallest ISAs. So we want an ISA that works well for a simple in-order design, decoupled, superscalar, sequential as well, right? Every kind of microarchitectural style. With the end of Moore's law, a big theme is specialization. So the only way to get better capability in all these systems is to build specialized engines. And that's why you see all those different cores on the modern SoC. But we want this ISA to be a good base to which you can add extensions as well. So it has to support extensive specialization. And perhaps one of the biggest features that's probably not as well appreciated is we really want it to be stable, i.e. it doesn't change and it doesn't disappear. One of the big problems with commercial ISAs is they disappear, not because of any technical failing, because of the business misfortunes of the company that's supporting them, right? So for example, there was this big important computer company called Digital Equipment Corporation, and they had a couple of very important instruction sets, VAX and Alpha. Both of those are gone now, and if you build a software investment around those ISAs, that's gone as well. Not because of anything you did, but because of, you know, the business fortunes of DEC itself, okay? So you want something that's stable, that's not going to change, not going to disappear. As we start talking about the Internet of Things, you're going to be embedding processors in concrete, and you're going to have to maintain them 50 years out. Right, so you want to make sure you're going to get a tool chain for that ISA in 50 years' time without paying exorbitant prices. Right? So RISC-V, we started this a long time ago in Berkeley, so I'll tell you how we got going. Back in 2010, my research group, every so often, we build a new set of students come in, we start a new set of projects, we do a review of what are we going to use as the ISA as the basis for this next set of research projects. So back in 2010, we've used a lot of different ones, MIPS, SPARC, x86, random other ISAs. Back in 2010, the obvious choice were x86 and ARM. They were dominant then, they're still dominant now, even more so maybe. But if you look at these choices, well, x86, it's clearly impossible, right? Just way too complicated, has these strange IP issues, right? Intel doesn't want other people building this. Now, every so often, I get this fantasy of building an x86, right? And when I go do that, I crack open the assembly code manual and look at the first opcode. So what's the first opcode? AAA, right? So what is AAA? It must be important. It's right at the front, right? ASCII adjust after addition, right? This is the first opcode in x86. So what does this important instruction do? Well, one register is a default source and destination, AL. If the low nibble is greater than 9 decimal, right, or the auxiliary carry flag is set, add 6 to the low nibble, discard the overflow, and increment the high byte of AL, and set the carry flags, right? Else, clear the carry flags. This is obviously a very important instruction because it has a single byte encoding in x86. Okay, so this is what I mean by the existing ISAs are dismal. So you look at this and say, this is crazy, no way I'm going to subject my students to this, all right? So how about ARM? The R in ARM stands for RISC, right? Sort of. Well, ARM is just mostly impossible, to paraphrase Doug Adams, right? It's, the time we looked at it, it didn't have 64-bit, it does now. Very complicated, and even worse IP issues, right? There's a joke about, the smallest time in the universe is the time between a light turning green and the New York cabbie behind you hitting his horn. That's not true. The smallest time in the universe is you putting up an open source ARM core and getting a letter from an ARM lawyer, right? So IP issues, very, very strong, right? Anyway, back in summer 2010, we started a 3-month project to develop our own clean slate ISA, and so I just want to give a shout out to Andrew Waterman, Yunsub Lee, and Dave Patterson, who are the co-principal designers of RISC-V, plus we had a lot of help from many other people. Okay, so we started this project. So it's going to be a 3-month project. Over the summer, we'll design an ISA and just use it internally for our own projects. 4 years later, we finally released the frozen base spec. It took a while, a lot longer than we thought. Now, this wasn't because we sat in a room pontificating about ISA design for 4 years. We did some of that, but along the way, we did a lot of tape outs, a lot of iterations on the design, a lot of publications came out along the way as well. Now, while we were doing this, a strange thing started happening. We started getting random emails from people all around the world saying things like, why did you change the spec? Our first reaction was, who are you? And second, why do you care, right? This is just a Berkeley internal project. And what had been happening was others had been seeing this, downloading the code and using it in projects. And quite often in the classes, we'll deliberately change the ISA because we want the students to do some exercise, right? We change things around. And they were complaining because we'd had class projects with differences in the ISA. So it was clear this was getting used and there was a need out there for something. So we started more seriously pushing it out around 2014. So why would you want to use RISC-V? Why is it RISC-V? So people ask me about the name. And first of all, it's RISC-V, even though it's spelled with a Roman numeral V, because the first RISC chip, RISC-1, is called RISC-1 and not RISC-I. And this isn't RISC-II, this is RISC-2. Okay, that's why it's called RISC-V. So posthumously, we renamed SOAR to RISC-3, SPUR to RISC-4. Dave Patterson always regretted dropping the name RISC from these later projects, so we kind of reinstated it. And so this is the first RISC-V chip we taped out back in 2011. So that's why we call it RISC-V. Right? It's the 5th iteration of the RISC architectures from UC Berkeley. So what's different about it? It's very simple. It's far smaller than the other conventional ISAs. It's a very clean slate design. We separated the user and privileged ISA pretty much completely, which is a flaw you'll find other commercial ISAs. They don't do that well enough. We also avoid microarchitecture or technology-dependent features in the design of the ISA. And it's designed as a modular ISA. So there's a small base and a set of standard extensions you can add to the base. And the goal of modular ISA is to get the maximum reuse from software for different kinds of chip you want to build. It's designed for extensibility and specialization. So in particular, it has a variable length instruction encoding. And there's a vast opcode space available to add those extensions for those customized accelerators. The other thing is it's stable. When we pushed this out to the community in 2014, we froze the spec. So the user level ISA is not changing. It's done, over. There's not going to be a version 8, a version 8.1, version 8.2, version 8.3. It's done. 2.0 is done, and it's frozen. We view that as a very important feature for the general purpose mandatory base set. There will be modules and extensions, but those will be modular, and all the tools will continue to work for that frozen base forever, is the idea. So let's go through what actually is it. On the first glance, it's a very traditional basic RISC ISA. So we have 4 base integer ISAs differentiated by the address width. So RV32, RV64, RV128. So 32-bit, 64-bit, 128-bit address-based versions. For RV32, there's one variant that only has half the registers for very, very tiny microcontrollers. Those base instruction sets are just integer only, and there are less than 50 hardware instructions to implement those. But those are enough to run an entire software stack, including GCC, position-independent code, dynamic linking, running an OS. Right? That's all you need to get going and have all of the modern software stack available to you. And the idea is if you want to do an accelerator, you might just start with only that, then add your own stuff to the side. Or we added a bunch more standard extensions to get you up to a full-featured ISA you might use in the basis of a Linux applications processor. So integer multiply divide, atomic memory ops, signal double precision floating point. And that combination we call G, IMAFD, and that's meant to be a reasonable general purpose ISA you can use for lots of things. And all of these are pretty standard RISC encoding in a fixed instruction format. And as I said, all these got frozen in 2014. They're not changing. So the encoding was designed very carefully. It's very simple. Took a lot of work to make it this simple. The register specifiers are all in the same place. They don't move around. Immediate to sign extended from the same bit in the word to improve the speed. Very simple encoding. So just to go through some of the features that are more interesting, the atomic operations extension adds two classes of atomic operations, fetch and op, and load reserve store conditional. So the fetch and ops, well, actually, for all the AMOs, one feature we did, now that the language community seems to have settled down on release consistency as a model for parallel code, we've added 2 bits to each instruction to let you set acquire and release consistency ordering on these AMO instructions. Now, one thing that's different about this versus a regular RISC is it supports a variable length encoding. Though in the base ISA, you can just deal with 32-bit fixed width encoding. If the bottom 2 bits of the instruction are 1, 1, it's a 32-bit instruction or greater. If they're not 1, 1, then it's a 16-bit instruction. Now, we originally did this primarily to add the compressed instructions, which just mix in with a regular 32-bit encoding. They're not a separate ISA. They're just an extension to the base ISA. And the only penalty we paid for supporting this variable length instructions is we lost 1 bit of range in branches and jumps in the base ISA, but we felt that was a good trade-off. Right, so we support variable length encoding, and the primary use right now is in the compressed instruction set. So the compressed code is really important for low-end, embedded, where you're trying to save code size, but it's also very important for high-end workloads where you're trying to reduce dynamic instruction cache footprint. So this is very similar to the other compressed ISAs, but one of the caveats to make this simple is that every compressed instruction expands to exactly one of the other instructions. There's no, so this makes the expansion very simple. It's like about 700 gates to build this expander. So only a tiny fraction of a small core to add this compression. And we feel it's pretty good. We get about 25 to 30% smaller code size when we add this compression in. And that's about the same as other compressed ISAs. So just to give you a comparison, this is looking at spec-int compressed for 32-bit architectures and 64-bit architectures. So for 32-bit architectures, the code size is about the same as Thumb2. For 64-bit, we're considerably smaller than all the other ISAs because they don't have compressed extensions up there. And x86 grew quite a bit when it went to 64-bit, right? So one sort of stat I'll pull out at random. So the compressed 64-bit fetches 8% fewer dynamic bytes than x86 64, right? So quite a lot less instruction traffic. We also have a vector extension that is in progress, and this will replace the SIMD, packed SIMD extensions that other ISAs have. We want to do a true vector style extension a la Cray. We view this as the right way to do vectors, so we don't need hundreds of opcodes, one for each width of vector register. So this is coming out pretty soon. I'll just mention this right now. In designing the privileged architecture, we also took a clean slate approach and made very clean separation between different layers of the stack. So RISC-V has different privilege modes: machine mode, hypervisor mode, supervisor mode, user mode. Machine mode, the lowest mode, is really meant for using for secure execution and secure boots. The OS never runs down there. It always runs up in a protected domain, but it only communicates to hardware via what we call an SBI, a supervisor binary interface. And the same for the hypervisor. It doesn't talk directly to the hardware. It talks via a hypervisor binary interface down to the hardware. And the whole architecture is designed to support extensive virtualization. This is still a work in progress, but we're building this out, this support out. So it's a very simple ISA, and just to hammer that point home, here's our building up of all the ISAs on one slide. So here's the instructions. This is the instructions for RB32. The base set, we had a few more for the privileged architecture. Then we had multiply divide. We had atomics, single, double, and quad precision floating point, compressed instructions, and then we can throw in the other address widths, 64, 128-bit address space. And by the time we're done, this is the whole instruction set on one slide. And it's pretty readable from here. I can read every instruction on that slide, and that's the entire instruction set. So the joke is, you know it's a RISC because the instruction set doesn't need, the manual doesn't need a staple, right? So fits on one card. Now what you might be thinking back in mind, this is all great, but this is kind of a toy academic thing. As I go talk to people, there's this notion, it's too simple. How can this be, there must be a reason that ARM V8 has 6 times as many instructions in there, right? Well, the answer is it competes pretty well. And here's some data. This is like Spec Int 2006, everything compiled with the same version of GCC, tuned for each architecture. And what you have on the y-axis is how many dynamic instructions are executed, normalized to the x86-64. And what you see is the rightmost 2 bars are the 64G. It's around the same number of instructions executed as micro-ops executed on the x86. If you think about the amount of microarchitectural work the core has to do, that's a fairer measure than the actual instructions fetched. Compared to the ARM, it looks like it's doing a bit more work, but the ARM V8 actually needs micro-ops to implement some of their instructions, and we don't have a way of counting that right now. But we assume that's going to be more similar to the x86 by the time we account for it. So basically, with many fewer instructions in the instruction set, we're executing roughly the same amount of microarchitectural work. So you're not paying a penalty in terms of doing more work, needing more functional units to complete this code. It's very competitive with existing industry ISAs. And there's big advantages to simplicity, right? Teaching. One of the goals of this was to make it easier to teach classes. Making it simple makes that a lot easier. Learning, it's a lot easier to learn it if it's simpler as well. Area, energy, QOR versus design time, verification, security. It's much easier to prove things about it when it's simple. Reuse. And so this point about the base ISA is so small and simple, it's fine to just take that, get all the software stack, then add your accelerator stuff on the side, right? That was one of the design goals, right? So many advantages to simplicity. So Berkeley, like I said, we did a bunch of tape-outs using RISC-V. We've actually done 12 chips, I think, 12 tape-outs so far in 28 and 45 nanometer, various foundries. And over time, these are pretty competitive with industry chips in terms of their performance and energy efficiency. So this is what we use to tune the ISA as we're going through. So just to give you some numbers, these are the open source cores available from Berkeley for doing RISC-V. Rocket is an in-order core. It's very comparable to like an A5. And then we have an out-of-order core generator, Boom, that gives you cores that are comparable to an A9 or an A15, right? So go ahead, download those. They're all free. Now, there's been a lot of interest in RISC-V, and I'll switch gears and tell you about the foundation. So this was a research project at Berkeley. We're continuing to be very active in RISC-V. We designed this to build our research infrastructure. But to get this used in industry, we wanted something a bit more stable, long-lived, that people could rely on. And so we created the foundation. So this is a 501c6 nonprofit trade association founded last year. We recruited Rick O'Connor, executive director. So the principles really are that the RISC-V standard is going to remain open and license-free to everybody. The compatibility suites will remain open for everybody. But if you want to use the RISC-V trademark in a commercial product, you have to be a member of the foundation, and you have to pass the compatibility suites. That's the way we're avoiding fragmentation in the community. Though there's no legal recourse. If you want to go take the ISA and develop your own thing, you can just go off and do that. But if you want to say it's RISC-V and use a trademark, you have to be a member of the foundation and be compatible. Okay. So foundation membership, we've been doing very well. This is the current snapshot of some of the members. So I'll just point out IBM, Google, NVIDIA, Oracle, HP, Western Digital, Microsemi, Draper, Mellanox, our little startup, Sci5. A lot of people, a lot of big companies have joined up. There's even more big companies. By July, we'll be able to announce a lot more companies in this foundation. Many of these are actively developing RISC-V cores for use at their company. So it's pretty widespread industry already. If you want to learn more about RISC-V, go to the website, riscv.org. We've had 3 workshops all sold out. The 4th one will be at MIT in July next month. So I think there might still be space if you want to go register at riscv.org and go to MIT, see the workshop. Just the highlights from the last workshop we had in January. This was held at Oracle, Oracle's conference center. Some highlights for me were Google saying that core boot doesn't commit unless the RISC-V port commits, right? It's actually a blocker on commits to RISC-V. HP Enterprise saying they're doing a UEFI port to RISC-V. It's not the kind of thing you do for fun. They're off doing that. And Jan Gray had this great result of, I thought this was just super cool, 400 RISC-V cores on a single FPGA. Aggregate performance over 1 MIPS per LUT. So yeah, like I said, the next workshop will be in MIT, so come along to that. The Global Semiconductor Alliance just did a report. So there's been a few talks here about open source hardware. I view, this is really a trend. We have to figure out how to make it easier for people to build chips and cut the cost. And open source is part of the story. And in this article, sponsored by Rambus, they talked about RISC-V being the Linux of processors. Because if you look at IP, processors is one of the most expensive pieces right now. So we really want to cut the cost to make it easier for people to do things. So why should you use RISC-V? Well, it's free and open. There's no proprietary lock-in. But it's not just free. It's also good, right? It's actually better than the other ones out there. It's stable. It's not going to change or disappear. There's no company to pull it out from underneath you. It's much simpler than the others. You get better QOR with this thing. And you can use it as the base ISA for every SoC, core on the SoC. It's readily extensible, right? So our modest goal at this point is really just to become the industry standard ISA for everything, right? And we're kind of well on the path to getting there. It'll take a few more years, but progress has been pretty rapid. All right, so with that, I'll stop, thank the sponsors, and happy to take any questions if we have time.
So we do have time for some questions. And use a microphone.
Okay,
go ahead.
Thanks. Okay, hi. On the privilege modes, I mean, obviously you've done support for hypervisors there. There's a growing trend in the server side for using containers, which kind of dumps a lot of the VM infrastructure and the hypervisor stuff. Do you see that affecting the privilege modes and adding to that, or do you see it more of the sort of going in the clear Linux direction where some of that hypervisor stuff just gets reused for the sort of container infrastructure?
Yeah, I think one thing is what we've seen is some of the features we had, having this separate machine mode below supervisor mode actually gets at some of the use cases that people are using hypervisors for. Our machine mode can actually contain an OS already. So I think the way we designed it means there's less need for hypervisor, and we haven't actually filled that in yet because we don't see a big demand for that right now because of the other features. If you design things differently, you might not need as much hypervisor support. Yeah, I agree. Any other questions?
You mentioned the compatibility suite that people need to pass to get the standard. Can you say a few more words about it and what it includes, and do you have documents describing it?
Yeah, the compatibility suite is a work in progress. So there's a bunch of assembly test codes that test the different instructions, and then there's also a constrained random instruction generator that you can use to help verify your cores. We'd love more donations to more stuff in that suite. We are building it out, but yeah, basically it's per instruction test to tell you whether you've supported that instruction according to the spec. Yeah.
Yeah, I guess what about tools to support software development, all the tool chains, simulators, stuff like that?
So the question was about tool chains. So in a few minutes, I have to run upstairs to help cover the RISC-V session. I'll give a talk there about the RISC-V software ecosystem, but basically all the open source stuff is there. So Linux, GCC, binutils, glibc, FreeBSD, LLVM, QEMU. There's a whole world. And the nice thing about being an open source ISA, a lot of people are attracted to this platform, and the software developers have been filling it out, that whole world out. So the tooling is coming on quite nicely. Like I said, HP is developing UEFI. Google's doing bootloaders. A lot of people are filling out that ecosystem.
Do you provide reference implementations or just the specifications at this point?
So there's a thing called SPIKE, which stands for Golden Spike, which is a C reference implementation, golden model of the ISA. Right. Yeah, there's a session right after this which has in-depth answers to those questions.
Wait, there is a question all the way.
Are there any development platforms out there for this?
Any development platforms? So there are, there's FPGA bit strings you can download right now, but the primary development platform people use for big software is QEMU. So people develop their operating systems inside QEMU. That runs at around 1 giga instructions per second on an x86 server. So it's pretty fast for doing software development.
I want to know if it was a hard decision to allow variable length encoding.
No. You need compress. You need compress code.
Any other question? I think we're good. I have one little question. What does it take to become a member of the foundation?
So if you want to be a commercial member, I think the minimum level, I should know this, is 5K. And that gives you license to sell products with the trademark. There's lower rates. There'll be an individual member rate of $100 for individuals to join. And also for auditors and universities who don't necessarily want to make products, there's an even lower rate.
Good.
I think it's like 2K a year.
Okay. Thank you very much, Krista. And we'll be upstairs.
Okay, thanks.